Okay, in this video I'm going to be talking about how to solve second order and higher ODEs numerically. So far we've covered how to solve first order ODEs. So let's just remember, I'm going to just write down general first order ODE. So y prime is equal to some function of the independent variable, which I'm going to call t, and y, and then we need an auxiliary condition to solve this. We need at least one for an initial value problem, and in fact all first order ODEs could be considered initial value problems because you only need one auxiliary condition. Let's just say y at 0 is equal to y naught. Okay, so this corresponds to some differential equation that has a solution, y sub t, that's at the value of t equal to 0. It has some initial value y naught, and maybe the exact solution looks something like this. It could look like anything. It's a whole family of curves defined by this function right here, f of t and y. So remember, y prime here is just equals dy dt. Okay, and f of xy could look like f of ty could be any function of t and y. So it could be equal to, I don't know, y minus t squared, or it could just be equal to y, or it could be equal to just a function of t cubed. It doesn't matter as long as it's only a function of just t and just y. Okay, so that's first order ODEs, and I've talked about how to solve these using numerical methods. We talked about a whole family of methods called Runge-Kutta methods. So Runge-Kutta methods. That use a formula basically that looks like this: y at I plus 1 equals y at I plus phi times h, where phi here is an estimate of the average slope over the interval. Oh, that's not how you spell interval. Interval. Xi to xi plus 1. So just a picture so you can picture that. Sorry, I guess I should these really should be t's, okay, because I need to keep my notation consistent, so just cross these out, okay, and this is really ti, and this is ti plus 1, okay, that's the interval. So y sub t, if we start out at t0, this is y0, this is t0. So then t plus 1, if we start at t0, it's going to be t1. And maybe our function looks something like this. And so the average slope over this interval would be the line drawn between these 2 points. The slope of this line would be the average slope. So maybe draw this curve a little bit better with a little bit more curvature to it. something like this. Okay. So then the average slope here looks something. It's the slope of this straight line connecting these 2 points. Alright. So if we can figure out that slope, this is called phi magic. It's the slope that'll give us the exact answer if we employ this formula right here. So all Runge-Kutta methods are based off of this general idea. Alright, now all of this was to solve first order ODEs. So I've been talking in kind of a long roundabout way of first order ODEs just to kind of give us the context. But really what we want to talk about is second order and higher ODEs. So remember, the order of the ODE is corresponds to the order of the highest derivative that shows up in the differential equation. So if I have a differential equation that's y double prime plus y prime minus 2y equals 0, the question might be asked, you know, what is the order? What is the order of this differential equation, of this ODE? And the answer is it's second order, because the highest order derivative is the second derivative. There's no third derivatives or fourth derivatives with respect to the independent variable. So we say it's second order. Second order. Alright, so if I have y quadruple prime minus y, sorry, that's triple prime, quadruple prime equals 0, this differential equation is fourth order. Okay? Fourth order. Now, we spent a lot of time learning how to solve first order differential equations, and the reason is because we can take any, and this is important, so I'm going to write it down, we can take any nth order ODE, so, and represent it as a system of n coupled first order ODEs. Alright, so this is an important concept to know and be able to apply right here, because it allows us, if we run into higher order ODEs that we want to solve, well, we can use the same methods that we use to solve first order ODEs, because we can simply take that higher order ODE and write it as a system of first order ODEs. So let's do an example to make this more clear. So one second order differential equation that comes up in engineering, is the equation that describes the motion of a mass on a spring. So if I have some spring, and I'm going to draw a terrible spring here, with some spring constant K, and this is some mass M, and we'll say there's a coordinate here, y, that represents the displacement of the mass from its equilibrium position. So y is the displacement from equilibrium. Then we can describe the displacement from equilibrium using this differential equation. We get mass times y double prime, which is the acceleration. So the second derivative with respect to time here, plus the damping coefficient times y prime, plus the spring constant times the displacement is equal to the mass times the acceleration of gravity. You can look at this. This is Newton's second law, or this is just saying mass times acceleration right here. Mass times acceleration is equal to the sum of the forces in the y direction. So actually, I guess I should write these terms on the other side. Let's go ahead and do that and just write this differential equation in terms of the acceleration. So divide everything by the mass. So I'm going to divide by the mass on this side and divide by the mass on this side. Okay, and rewrite this. So I get y double prime, or the acceleration, is equal to the force of gravity, m times g. Oh, and I forgot, I'm going to divide by the mass, so I'm just going to put this as g minus c over m times y prime minus k over m times y. Alright. So this is a second order differential equation that describes the displacement of this mass from its equilibrium position. So second order ODE, right? So instead of using calculus to solve this, we want to solve it numerically. So what we're going to do is we're going to write this right as system of two, let's write this out, two first order ODEs. Alright, so to do that, I'm going to introduce two new variables. Okay, so I'm going to say y1 and y2 are going to be my new variables, and y1 is just going to be equal to the original displacement. Okay, and y2 is going to be equal to the velocity, or y prime. Okay, so these are my two new variables, and so because of the way I've defined them, I can say the following. If I differentiate y1 with respect to t, I get y1 prime, and that's going to be equal to literally y prime, because I defined it to be y, so it's going to be equal to y prime, but that's just y2. Okay, y2. So I want to write my new set of differential equations in terms of my new variables only. I don't want any y's showing up here, so I just want y1s and y2s. And now if I differentiate y2 with respect to time, that's going to be equal to y double prime. Well, I have an equation right here that describes y double prime, and y prime here is just y2, and y is just y1. So I can substitute those in and write down an equation for y2 prime in terms of y1 and y2. So if I do that, I get the following. I get g minus c over m times y prime, which is just y2, minus k over m times y, which is y1. Alright, so these, now I have, this is two differential equations that are both first order. So they're first order because the highest derivative for each of the variables is just the first derivative. So y1 prime is y1 prime is just equal to dy1 dt, right? That's first derivative, so it's first order. And then I've got y2 prime is equal to dy2 dt. Now I forgot to introduce auxiliary conditions for this problem, and so each of these ODEs need an auxiliary condition. Because this is second order, we need two auxiliary conditions here. So I could say my auxiliary conditions. I need an initial condition for the displacement. I could just say it's equal to 0, so it starts out at equilibrium. And I need an initial value for the velocity. I'm just going to say it's equal to 0. So that would correspond to my mass starting from rest at equilibrium position, and then you just letting it go and watching it kind of bounce up and down and oscillate. Now I could change these initial conditions to model different scenarios, like what if I push the mass down with some initial so I gave it some initial velocity, or I could say what if I stretched it down, kind of stretched it away from its equilibrium position and then just let it go. That would correspond to some non-zero initial displacement with an initial velocity still equal to 0. So anyways, but the question is how do these translate into auxiliary conditions for my new system of first order ODEs? Well, I can just write those down here. Y1 at 0 is going to correspond to y at 0 equals y at 0, which just equals 0 for this case, or you could say in general just why not. And then y2 at 0 corresponds to y prime at 0. This is y prime at 0, which is just equal to 0. Or you could say that's just the initial velocity, y prime naught. Okay? Sorry, I'm kind of making this messy here. Oh. There's a line here separating this box. Alright, so now I've got an auxiliary condition for both differential equations. For this differential equation right here, and this differential equation right here. And those auxiliary conditions are down here. Okay? Alright, so now I could take this and I could solve these simultaneously using a method like any of the Runge-Kutta methods. I'm going to show you how to do that in another video, but I want to go ahead and make sure that this idea of transforming an ODE to a system of first order ODEs is clear. So I'm going to do a couple more examples. So what if I have y triple prime minus y plus t cubed, I don't know, plus y double prime times the sine of t equals 0. That's a pretty crazy looking differential equation. I might ask you, first of all, what order is it? Well, what is the highest derivative that shows up? It's this one, which is y triple prime. So the third derivative with respect to time, so that means it's third order. Okay, it's a third order ordinary differential equation. Now, because it's third order, that implies we can transform it into a system of 3 first order ODEs. Alright, so let's go ahead and do that by just defining some new variables. I'm going to define y1 to be equal to y, y2 to be equal to y prime, and y3 to be equal to y double prime. Now, that implies the following differential equations. y1 prime is just going to be equal to y2 because of the way we defined it. y2 prime is just going to be equal to y3. And then y3 prime is going to be equal to y triple prime, which is right here, which we can solve for that and put all these other terms in terms of our new variables. So substitute y1 in for y and substitute y2 for y prime, and we'll get the following equation. Let's see if, I need a little bit more room. Oh, I want to still see my differential equation. So if I do that, I'm going to get it's equal to, so positive y, which is going to be y1 minus minus y double prime, which is y2, minus y2 times the sine of t minus t cubed. Alright, now I would need auxiliary conditions such as y at 0 equals something equals y naught, y prime at 0 equals y prime naught, and y double prime at 0 equals y double prime naught. And those three conditions would correspond to the auxiliary conditions for this system of first order ODEs. Alright, so those are the system of ODEs. Technically their auxiliary conditions are part of that system, so I would say y1 at 0 equals y naught, y2 at 0 equals y prime naught, and y3 at 0 equals y double prime at times 0. Now these just be numbers for a specific problem. Okay, these are all going to be will be numbers. Okay, or displacements. Well, this will be a displacement, this will be a velocity, this will be an acceleration, if you're thinking in terms of a physical system, not just some mathematical world. Alright, so I would expect you after watching this video that you should be able to take any differential equation of higher than first order and transform it into a system of first order ODEs.
So you should be able to do this problem. Y prime 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 minus y triple prime plus sine t squared divided by y squared minus y times t to the 1/2 equals the exponential of t cubed. You should be able to take this right here and write it as a system of first order ODEs. Okay, so try it out, do it. Okay, this one would also have some auxiliary conditions. It would have y at 0. I'm just going to plug in some numbers. Y prime at 0 equals 1. Y double prime at 0 equals 2. And y triple prime at 0 equals 0. Alright, given this set, go ahead and try it out. You should be able to write this as a system of first order ODEs, even though it looks nasty and complex. You can do it. If you can't, then I haven't taught you anything in this video. So hopefully you can. I'll see you in the next video where I show you how to do this in MATLAB. Actually solve a system of first order ODEs using Runge-Kutta methods.